In the LHC, we accelerate particles to phenomenal energies along circular tunnels. We collide them, and we study the secondary particles created by the collisions. In this video series so far, we focused a lot on the magnets, which deflect the particles so that they go round and round in the tunnels. But in today's video, we are going to shine a light on what gives them so much energy in the first place. We're going to put the accelerator in particle accelerator. It turns out, to figure out how the accelerating components of the LHC work, we need to understand wave physics. Waves are everywhere around us. We see them in the ripples on a pond, feel them in the beat of music at a concert, and even find them to be the heart of atoms. And at the quantum level, objects seem to behave in a confusing way, sometimes like waves, and sometimes like particles. So, today, we're going to tackle this particularly wavy matter. And in doing so, we're going to stroll through rolling fields of grass, meet platypuses, and put off going to the dentist. So hang on, it's going to be quite the adventure. In this video, we will first study classical physics and understand what behaving like a particle or behaving like a wave means. Then we'll move on to quantum physics and figure out what the wave-particle duality of matter and light is all about. Then we'll find out how CERN engineers use waves to accelerate particles in the LHC. Let's go. Here is a ping pong ball. Whether it's at rest or in motion, we can always precisely point to where the ball is over time, so we can clearly define its trajectory. We say that it is localized in space. Here are ripples at the surface of a small water tank, created by a dipper vibrating up and down very fast. Looking at their shadows from above, we see that the ripples extend from the dipper to the entire surface of the water. They don't have a trajectory. We say that they are spread out across space. The ping pong ball displays particle-like behavior, while the ripples at the surface of the water display wave-like behavior. These are the only two types of behavior recognized by classical physics. In classical physics, particle-like behavior is quite straightforward. It's just like what a ball does during a game of pool. Wave-like behavior is a bit more tricky to grasp. To get a better picture, let's study a bit of wave physics. A wave is a group of coordinated oscillations. There are two main types of waves: traveling waves and standing waves. This is an example of a traveling wave, and this is an example of a standing wave. These examples show two different patterns of coordinated oscillations, two different ways for the various spots along the rope to vibrate up and down over time. Traveling waves are characterized by a disturbance which moves across space at a specific velocity, here from right to left. But the rope itself is not moving from right to left. All of its parts are still only oscillating up and down. So, a traveling wave does not carry matter along. As the disturbance passes, matter only oscillates in place. A great way to see this is when the wind blows ripples in a field. The individual blades of grass are firmly planted in the ground, yet a wave travels across the field. Standing waves are characterized by a fixed pattern of coordinated oscillations. There are spots of maximal oscillation, which we call antinodes, and spots where there is no oscillation at all, which we call nodes. And they always stay at the same place. When we play the guitar, we create standing waves on the strings, and by putting our fingers on different frets, we are choosing where the nodes and antinodes of the wave are. A wave is always the sign of a feedback loop between two physical quantities. In other words, a change in one quantity over time triggers a change in the other across space, and vice versa. For the waves we've seen so far, these quantities always boil down to potential energy and kinetic energy. If you push a spring, you see a disturbance travel across the spring. Elastic potential energy and kinetic energy are being exchanged between the point of compression and the surrounding points. And it's happening over and over again at each point that the disturbance reaches. So, in one word, waves are loopy. Loops and cycles are at the core of what a wave is. Most of the waves we're interested in actually involve repeated disturbances happening over and over. So, physicists have come up with a set of tools to describe how repetitive a particular wave is. All waves have high points, where the oscillation goes higher than anywhere else, and low points, where the oscillation goes lower than anywhere else. These are the peaks and the troughs of the wave. The length between any two troughs, or the length between any two peaks, is the same, no matter where you measure it on the wave. So we simply call it the wavelength. The wavelength of a wave is the distance between two identical points on the wave. For example, the distance between two peaks or the distance between two troughs. The frequency of a wave is how many wavelengths pass by a point in 1 second. Now that we're a bit more familiar with waves, we can move on to two key differences between wave-like behaviour and particle-like behaviour. Let's first see how objects behave at an obstacle with a small gap. Here's a series of ping pong balls, and here is an obstacle with a small gap. We see that the balls which go through the gap continue in the same direction. So far, physics is almost boring. Let's make it more exciting with water waves instead of balls. Let's add walls with a gap to our water tank. When the waves hit the gap, they don't just continue in the same direction. They spread out. Past the gap, they go in many different directions. This phenomenon is known as diffraction. Diffraction is the deviation of the direction of travel of a wave which occurs around the corners of an obstacle. It's only visible if the wavelength of the waves and the width of the gap are about the same size. Diffraction is a good indication of wave-like behaviour. If you see diffraction, that means you're dealing with waves. There is no diffraction in particle-like behaviour. Balls which go through a gap continue in the same direction. Now, let's study how objects collide. Here's one ping pong ball. Here's another ping pong ball. Here are the two balls together. They bounce off of each other. Now, here's one group of waves. Here's another group of waves. Here are the two of them together. They pass through each other. This phenomenon is known as superposition. Superposition is the idea that when two waves meet, they simply combine into a new wave. This new wave usually has interesting features. When our two groups of waves meet, the waves resulting from the superposition are very large in specific regions of the water. This is known as constructive interference. The two waves both meet at a peak, making a new, higher peak, or they both met at a trough, making a new, lower trough. We also see that in other specific regions, the superposition leads to almost no waves at all. This is known as destructive interference. The peak from one wave met at a trough from the other wave, cancelling both of them out. Interference is another sign of wave-like behaviour. If you see interference, then again, you know that you're dealing with waves. There's no interference with particle-like behaviour. When we bounce two balls off each other, they don't make another massive ball. And they certainly don't vanish into thin air. That'd make it pretty hard to play pool. Alright, so in this section, we've seen what wave-like behaviour is and how it differs from particle-like behaviour in classical physics. Objects which are spread out, which can diffract and interfere, have wave-like behaviour. Objects which are localised, have a clear trajectory, and neither diffract nor interfere, have particle-like behaviour. It's time to leave classical physics behind us and put some quantum objects to the test. In this chapter, we'll focus on photons and electrons. At CERN, we know them as two very important members of the standard model of particle physics. Now, we could show you that, of course, we should use particle-like behaviour just like we defined in the first chapter to model photons and electrons in many experiments. But today, our focus is on waves. So let's see if we can find any experiments where we should use a wave-like behaviour model instead for photons and for electrons. Let's start by making a beam of photons. The best way to do that is to use a laser. Lasers are unique sources of light because they emit photons with precisely the same energy in precisely the same direction. Let's see what happens to the beam if we add an obstacle in the path of the light. We'll use a screen with two very narrow slits in it. When we shine the laser through the slits, we see that the light forms a complex pattern on the wall on the other side. Clearly, we're not seeing two bright slit-shaped spots, so the light changed direction when going through the obstacle. And also, there are bright spots and dark spots, so that means light added up in some areas and cancelled out in others. So here, we're seeing both diffraction and interference of visible light. What we saw with the two groups of water waves is really the same type of pattern as what we're seeing now with light and two slits. So this experiment proves that sometimes we need a wave model to describe photons, particles of light. Now, let's make a beam of electrons. If you've watched the first video in our electromagnetic adventures, you know that we can do that in a vacuum tube. For this experiment, we're going to use a slightly different model of a vacuum tube, but its working principle is the same. We heat up a little piece of metal at the small end of a tube. It emits electrons, which are accelerated through the tube by a strong electric field. So far, so good. But here's where there's something new. In this model of a vacuum tube, there's an obstacle on the path of the beam. It's a film of graphite, a crystalline form of carbon. The gaps between the atoms in the crystal act just like a series of thin slits. And so, we see quite a complex pattern on the phosphorescent screen at the large end of the tube. It tells us where the electrons ended their journey. There was a bright dot along the axis of the tube, so quite a few electrons went straight through the crystal. But there are also bright rings, meaning that some electrons were deviated by the crystal and hit the screen away from the axis. This is actually just like the pattern for photons. We're seeing diffraction and interference. The only difference is that our slits diffract photons in one specific direction, while here, the crystal diffracts the electrons in all directions. So this experiment proves that sometimes we need a wave model to describe matter particles, like electrons. That's kind of crazy. We have matter acting like it's a wave. So at this point, we know that sometimes we should model photons and electrons as particles, and other times we should model them as waves. And from what we know looking at water ripples and ping pong balls in the first chapter of this video, this should be impossible. We clearly saw that particle-like behavior and wave-like behavior were incompatible. If you behave like a wave, then you can't behave like a particle, and vice versa. Right? This seems like a paradox. To solve it, let's go to Australia. Australia is famous for its unique wildlife, which is often never found anywhere else on Earth. At the turn of the 19th century, when European scientists saw a platypus for the first time, they thought it was so weird, it had to be fake. Platypuses seemed impossible to classify. They feed milk to their young, like mammals, but they also lay eggs, like birds or reptiles. According to the classical approach to natural history at the time, these two behaviours were completely distinct and incompatible. But naturalists were forced to go beyond their classification system and come up with an entirely new category for platypuses: egg-laying mammals. There was only a paradox to begin with, because the scientists thought that classical categories applied to everything. This platypus business isn't so different from our case with waves and particles. In the same way, electrons and photons aren't just weird or paradoxical, they go beyond the two types of behaviour recognised by classical physics and fit in a category of their own, which we call quantum objects. We say that they exhibit wave-particle duality. Crucially, that does not mean that they have a dual nature. It's not that they are sometimes waves and other times they are particles. They have an unchanging singular nature, which we can't picture in our mind. There is only a duality in the way we model them, which can indeed change depending on the type of experiment we subject them to. Sometimes, quantum physics is not just about using complicated maths. It's also about a very precise use of language. Before quantum physics was a thing, physicists had known for a long time that light can display wave-like behaviour and that matter can display particle-like behaviour. Proving that each could actually show both types of behaviour was what was tricky. Explaining a puzzling experiment in which light showed particle-like behaviour got Albert Einstein the Nobel Prize in 1921. Predicting that matter could show wave-like behaviour got French theorist Louis de Broglie another Nobel Prize in 1929. And in 1937, yet another Nobel Prize was awarded to some of the experimentalists who confirmed his theory, diffracting electrons like we just did. De Broglie's wave theory of matter was refined by Austrian physicist Erwin Schrödinger. Using classical wave physics, he came up with the concept of a wave function, a mathematical description of the wave properties of all quantum objects. Interestingly, despite the fact that we find waves to be one of the core concepts of quantum physics, we're still not quite sure exactly what is wavy there. In the first chapter, we said that whenever we saw a wave, we could find two physical quantities trapped in a feedback loop. Schrödinger's wave function is a rare example where we see a wave, but we can't tell what the two quantities which give rise to the wave are. Okay, now that we've made some progress with quantum physics, let's get a sense of what high energy physics is. That's what we do in the LHC. We take quantum objects, most of the time protons, and we smash them together at high energies. So, let's get back to both of our diffraction experiments and let's boost the energy. We can change the energy of our photons by using laser beams of different colours. Red light corresponds to photons with the lowest energy in the visible spectrum, and we see that the beam is diffracted quite a lot. Green light is made out of photons with a bit more energy, and the beam is refracted a bit less. And blue light, with photons with the most energy in the visible spectrum, is diffracted the least. We can change the energy of our electrons by tuning the strength of the electric field. With a weak field, electrons are slow. We see large rings, so the electron beam is diffracted a lot. As we increase the strength of the field, electrons become faster. We see the rings shrink, so the beam is diffracted less and less. The rings are also brighter, but that's just because the same number of electrons get concentrated on a smaller perimeter. So, given the super high energies we work with at CERN, we don't have to worry too much about protons in the LHC diffracting or interfering. With high energy physics, stuff just gets less wavy. So that's why at CERN, we say we do particle physics. We should say we do high energy physics of quantum objects, but that's a bit too long to say. There is, however, always a specific spot in our machines where it gets very wavy, and that will be the focus of the next chapter. At this point in our series, we've talked a lot about the components of the LHC which deflect the particles. We've covered various aspects of the superconducting dipole magnets in several videos. In one of these videos, we've also glanced over the LHC components which accelerate the particles, those which increase their velocity, or give them more energy, if we want to be perfectly accurate. Today, it's time to go over acceleration engineering in more detail. The most basic acceleration technique works with two conducting metal rings in a vacuum. One ring has an excess of electrons, and the other has a shortage of electrons. Vacuum being an insulator, the excess electrons can't travel to the other ring. So we have an electric charge imbalance. This creates an electric field, and the field exerts a force on any electrically charged particles passing through, which accelerates them in the direction of the field. Here, note that we have a static electric field. The particles go through a field which does not change with time. This is very similar to how our electron beam is accelerated, and to accelerate our electrons more, we just make the electric field stronger. That's essentially 19th century technology. We can't push it too far. The electric field can become so strong that it will end up pulling out electrons from the surface of the metal rings. This creates a conducting path through the vacuum, which leads to an electric arc, a very intense and short-lived electric current that restores the balance of electric charge and destroys the electric field. This process is what we call electrical breakdown. Static electric fields can only be so strong before electrical breakdown happens. With this technique, the maximum energy we can accelerate particles to is limited. The LHC does not rely on this simple acceleration technique. It has radiofrequency cavities instead. The fact that the LHC has cavities doesn't mean that it needs to go to the dentist. Rather, a cavity is just a hollow or enclosed space. But when engineers use the term cavity, they're actually referring to a specially designed metallic shape that surrounds the hollow space, like this one. When a cavity is in operation, there's an oscillating electromagnetic field in the hollow space inside. Oscillations of electromagnetic fields are called electromagnetic waves. Like the waves we saw in the first chapter of this video, they can be described pretty accurately with classical physics. But unlike them, electromagnetic waves don't need to exist in a material. They can exist in a vacuum. That's good because that's also what we have inside a working cavity in a particle accelerator. You wouldn't want the particles you're trying to accelerate to bump into gas molecules and slow down. There are many situations when visible light can be modelled as an electromagnetic wave. The frequency of visible light is kind of out of this world. There are about 1,000,000 billion wavelengths that pass any point every second. Waves of the same nature, but with a slightly less crazy frequency, are known as radiofrequency waves. They only oscillate up to 1 billion times per second. We can't see them with our eyes, but we could pick them up with a radio receiver if we wanted. In the LHC's cavities, they oscillate 400 million times per second. Radiofrequency cavities are shaped like an ellipse. This interesting shape sort of separates the electric and the magnetic parts of the wave. Oscillations of the magnetic field are confined close to the round edge of the cavity, where nothing much happens, while the oscillations of the electric field are in the center, where the particles pass through. So let's just focus on the oscillations of the electric field from now on. They are simple standing waves, with one node on either side of the cavity and an antinode in the middle. This means that everywhere in the cavity, one moment the electric field is pointing to the right, and the next moment it is pointing to the left. And this is the reason why radiofrequency cavities shine. Oscillating electric fields can be made much stronger than static electric fields without risking an electrical breakdown. In the LHC's cavities, the electric field changes direction so quickly that electrical breakdown between the two sides of the cavity doesn't have time to happen. So now we understand that the LHC uses cavities with radiofrequency standing electromagnetic waves to accelerate particles. So let's see what they look like in the tunnel. This is what you'd see if you went to see them in the tunnel. Well, it's a bit like in this video, when we talked about the dipole magnets. In the tunnel, you can't see much of the actual electromagnets. All you see are blue vacuum tanks. It's the same here. These steel cylinders are also vacuum tanks. If we open up the cylinders, we see the cavities inside the tanks, with the particle beams passing through. And just like with the magnets, they're inside vacuum tanks because they're superconducting cavities. Superconducting cavities have to be kept below 10 Kelvin to work. They need to be shielded from the heat coming from the tunnel, and the vacuum tank is part of this shielding strategy. Superconducting cavities are very efficient at sustaining electromagnetic waves with a lot of energy. Now let's see exactly what happens to protons from the LHC when they reach a cavity. The first thing to know about the particle beams in the LHC is that the protons are not coming as a continuous stream, but as bunches, which are basically little clumps of particles. Now, if all the particles in a bunch don't have the same velocity, they're going to spread out like a pack of sheep herded by a lazy dog. The fastest particles pull ahead, and the slowest particles lag behind. The LHC is timed so that each bunch enters the cavity before the wave reaches its maximum oscillation. So that means that the first particles to enter the cavity won't get the strongest boost from the field. But these particles are already the fastest ones to begin with, so they don't need as much of a boost as the ones coming after them. As the wave gets stronger, the particles in the middle of the pack get a stronger boost, and the particles at the back of the bunch get into the cavity just as the wave reaches its maximum. This gives the largest boost to those who need it the most. And the LHC is also timed so that there are no bunches in the cavity at all when the wave swings back the other direction. That corresponds to a field pointing in the wrong direction, which would decelerate the particles. So, with a clever use of wave physics, cavities perform 3 jobs in one. They give the protons a very strong kick in the right direction, they never give them a kick in the wrong direction, and they keep them in tightly packed bunches. So, radiofrequency cavities are to protons what sheepdogs are to sheep. They not only get them moving, but they also keep them in nice compact herds. And with that, we hope we gave you a greater appreciation for the beautiful physics of waves. The next time you notice something wavy, take a moment to reflect on how the same physics sometimes helps us to model the behaviour of quantum objects, and is critical to accelerate particles at high energies. And now, it's time to wave you goodbye. Thanks for learning with us.